This video looks at the required properties of the pavement layer and the tests we undertake to confirm that the pavement we are constructing meets the specified requirements. Section 7 of TNZ B2 requires that the aggregate transport and laying methodology be planned to avoid segregation and contamination. Unbound granular aggregate layers, such as base coarse and subbase, rely on the coarse and fine materials being present in the correct proportions so the layer can lock together. The coarse particles support the loads while the fine particles fill the voids between the coarse particles and lock them in place. As we have seen in the pavement aggregate section, the grading of aggregates is carefully controlled so the correct mix is delivered to site. However, this mix is not going to work if the fine and coarse particles are separated during transport or if clay or dust contaminates them. Separation can occur through excessive vibration or movement, with the coarse particles tending to be more easily moved out of the mix when vibrated. One way of avoiding this is to lay the aggregate from a moving truck so that it's spread out in a layer, as we saw in the road construction section. This minimizes the amount of grading required to form the layer ready for compaction, and so minimizes segregation. Contamination can result from dust blowing into the mix or from stockpiling the aggregate in exposed positions for extended periods of time. Therefore, it is best to run the aggregate onto the road when it is delivered. This also avoids double handling the aggregate, which can cause segregation and adds time and cost to the laying operation. The aggregate layer needs to be thin enough to allow compaction through the whole layer, but thick enough to be a viable layer. TNZ B2 sets a minimum layer thickness of 2.5 times the maximum particle size. So a gap 65 subbase has to have a minimum layer thickness of 162 millimeters, while a gap 40 base course needs to be thicker than 100 millimeters, which is 2.5 times the maximum particle size, which is 40 mils. So 2.5 times 40 equals 100. You may have noticed this 100 millimeter minimum thickness on the chart we used to design a pavement in the pavement design topic. If you did the exercise, you would have noted that we ended up with a 70 millimeter layer of subbase, which according to this specification would not be suitable. TNZ B2 also sets a maximum thickness of 200 millimeters for the base course material to ensure the full layer is compacted. If the base course has more than 200 millimeters, then it would need to be laid in several layers, with each layer being compacted and tested before the next layer is laid. This may not be a problem with base course, but for subbase, the layer may need to be thicker than 200 mils, so it may need to be brought up in several layers. The aggregate layer also needs to be compacted to the required density. The aggregate layer gets stronger as it gets denser. This is because dense aggregate has more particles packed into it, which means more contact areas. The aggregate distributes and transmits the road loadings via the contact areas. So more contact areas means more strength. The aggregate also needs some water in the voids during compaction to lubricate the contact areas and allow the particles to slide past each other into a more dense structure. We will look at density and strength in the next few slides. Density is a measure of the weight of a material in a certain volume and basically how many aggregate particles you can jam into a set space. So if you weighed 1 cubic meter of sand and found it weighed 2,400 kilograms, then you could say it has a density of 2,400 kilograms per cubic meter. So 1,000 kilograms equals 1 ton. So you could also say that the density is 2.4 tons per cubic meter. In aggregates, the density varies according to how compact it is, how much water is present, and what type of rock was used to make it. Some rocks are denser than others, so the same size particles may vary in weight depending on their rock materials, although the variation is quite narrow for the types of rocks we use for aggregate. The diagram above shows two samples of the same type of aggregate of the same volume, but one weighs more than the other because more aggregate particles are packed into the same space, so the one that weighs more is on the right. The heavier sample, on the right, has a higher density because there are more aggregate particles packed into the same volume. More aggregate particles means more contact areas between the particles. Contact areas provide the strength of the aggregate, which is why the denser sample would be stronger because it has more contact areas between particles. This is what we're doing when we compact the aggregate. We are forcing the aggregate particles into a smaller space by pushing and vibrating them together. By making the aggregate layer denser, we are making it stronger. The maximum strength of an aggregate layer occurs when the layer is at its maximum density. Note that the void spaces in the aggregate reduce when we compact it. So that's how we can fit more particles into the same space. It should also be noted that the moisture content, that is the amount of water in the aggregate voids, has a strong influence on how compact we can make an aggregate layer. Water in the aggregate allows soil particles to slide into a more compact matrix. Therefore, if the soil is too dry, it needs to be wetted to the required moisture content that will allow it to be properly compacted. However, too much water results in the water holding the aggregate particles apart when they are compacted, and so not being able to settle into a compact soil mass. In this case, the aggregate is too wet, and so it needs to be dried. So the aggregate needs to be at a certain moisture content that is not too wet, not too dry, to allow it to be compacted to the required density and strength. This moisture content is called the optimum moisture content. So let's look at that in a bit more detail. The optimum moisture content and the corresponding maximum density it produces is determined in a lab test, which is shown by the graph where the moisture content is on the x-axis, the horizontal axis, while the aggregate dry density is on the y-axis, the vertical one. They are both linear scales. The test consists of a series of repetitive measures of the compaction achieved for samples at increasing moisture contents. So the aggregate sample is dried and then subjected to a standard compaction test. The sample is then dried and the dry density is determined. So you have the dry density for the sample at a particular moisture content. The sample is then wetted to a higher moisture content, that is, more water is added than in the previous test, and the compaction and density measurements are repeated. And you have the dry density for a sample with a higher moisture content. You add even more water, the next test, and repeat, and so on. The dry density is the density of aggregate without any water in the voids. We remove the water before weighing each sample so that the increase in quantity of water added as the test goes on does not obscure the actual density of the aggregate. Drawing a line connecting the sample results, gives us a curve which is called the standard compaction curve for that aggregate. You can see that the curve starts low. That is because at the lower moisture content, the aggregate is too dry and there is not enough water to lubricate the contact areas to allow the particles to slide into a denser formation. When we add more water, that is, the moisture content is increased, we get a higher density material as there is some water lubricating the contact areas. Even more water increases the dry density even more. But then the dry density achieved drops away as we increase the moisture content. There is now too much water in the voids and it is preventing the particles from coming closer to each other and forming a dense matrix. So there is a peak in the middle where we obtain the maximum dry density and hence the strongest aggregate layer. The moisture content is called the optimum moisture content, and that is what we want the aggregate to be at when we compact it. The dry density at that point is called the maximum dry density, and that is what we can expect the aggregate to be able to compact down to. There are charts that allow us to correlate dry density with strength, and so the designer can figure out what strength the aggregate will have in service. if it has that particular maximum dry density. This is used in pavement design. So we can measure the strength of the aggregate layer by measuring its density. Measuring density is easier than measuring the strength directly, so we measure density when compacting to give us an idea of how close we are to the required strength. We usually test the strength of the layer directly using CBR or other strength methods when we consider we have reached the required strength. The measurement of dry density in the field is undertaken with a nuclear densometer. This photo shows a nuclear densometer in action on an aggregate. The same instrument is used on soils, but uses a slightly different method, which we will look at in the road earthworks microcredential. The red box contains measuring equipment and a small amount of radioactive material. The handle to the right is the top of a probe which is pushed into the soil. The probe contains a small amount of radioactive material in it, which emits gamma radiation. The box measures the amount of gamma radiation that gets through the material. Denser soils stop more gamma radiation, while less dense soils let more get through. The instrument correlates the gamma radiation received with density and provides a reading on the wet density of the soil. The moisture content of the material being tested affects the dry density reading. So there is a second radioactive source under the control panel, which is used to measure the moisture content of the material. The instrument calculates the dry density by adjusting the wet density reading it has directly measured using the moisture content it is also measured. So a nuclear densometer gives you an estimate of the dry density and the moisture content. Section 7.5 of TNZ-B2 requires that the required compaction to be achieved using the least number of compactor passes. If there are too many passes, then the compactor could start crushing aggregate, especially if it is in vibration mode. However, too few passes will mean that the aggregate is not properly compacted. So the requirement of TNZ-B2 is that the subbase dry density is equal to or more than 95% of the maximum dry density which was determined in the lab for that particular aggregate. It also requires that the base course dry density is equal to or more than 98% of the mass dry density of that base course aggregate as determined in the lab. So we need to determine how many passes a particular compactor needs to make to compact the aggregate to its maximum dry density or close to it. This is done with a plateau test. The plateau test starts with measuring the density of the aggregate layer before compaction using a nuclear densometer. The compactor that will undertake the primary compaction of the aggregate then does one pass over the aggregate layer in vibration mode, and the dry density is again measured. The process then continues with the density being measured after each pass and the results being recorded in a graph of number of passes versus the dry density, which is shown here. The graph normally looks like this after a few passes. Note that the effectiveness of the primary compaction levels off into a kind of plateau, where additional passes do not result in any significant increase in dry density. The operator then knows that the number of passes required to get to the plateau and knows not to use primary compaction after this. So in this case, you would say about 4 passes of the compactor is what is required. The test area is then compacted using steel rollers or PTR in the secondary compaction process. This different type of rolling yields an initial increase in dry density, but the curve again levels off to a plateau after a few passes. This is the point where you stop compacting as you have achieved as good a dry density as you can, and additional compaction is only likely to start crushing the aggregate and breaking up the layer. So as mentioned, TNZ-B2 requires that the actual dry density after compaction be 95% of the maximum dry density. set out in the lab test for subbases and 98% of the maximum dry density for base courses. Another common test on pavements is the deflection. This is the measure of how much the pavement flexes under a heavy load. This photo shows a Beckelman beam test being undertaken. The beam is about 4 meters long with a pip in the middle, as shown on the drawing. One end is in between the two tires of the truck. The other has a dial gauge that measures very small movement. The truck has ballast, so the load on the pavement is about 8.2 tons over the whole back axle, which is the maximum load for a road. The road beneath the tires is compressed under the load. When the truck moves forward, the road surface lifts. The beam end lifts with the road, resulting in the beam tipping, so the dial gauge end drops. The amount of movement is measured by the dial gauge and the rebound calculated. This test gives you a pretty good idea of how well the road responds. If the rebound is too much, then the road is not properly compacted, or it is coming to the end of its life.